Place myself.
Yeah.
To the blue one.
Go around the table.
I go around the table. Yeah, well, I'm not the speaker. So it's a pleasure for me today to introduce our guest, Slava Lukin, who has been staying here already for a couple of weeks, or 3 weeks, and he is actually a visitor funded by Jesus program. So Slava is a plasma physicist, and he currently works as the program director of the NSF, National Science Foundation in the United States. So despite of his demanding job, for the last 7 years, he still has been finding time for doing science, which is good for us because he keeps to be our collaborator for several years already. So plasma physics is general in astrophysics, right? So Slava has been studying plasma from numerical point of view and also all different types of plasmas, because before his current job at NSF, he has been working as an astrophysicist at the Naval Research Lab for 5 years before that. And before that, he was also a postdoc at the Washington University. And before that, he made his PhD at the Princeton University, and he delivered it in 2008. So today he will be speaking about magnetic reconnection, which is a process common for many astrophysical plasmas. And that's basically it. So it's a pleasure for me to introduce you.
Thank you, Elena. Thank you for coming. Thank you for giving me this opportunity to give this talk. As Elena mentioned earlier, it's a little bit like a PhD defense, but the difference is that the PhD student usually knows what they're talking about because they've been working on it for a few years right before that. And as Elena mentioned, I primarily do program management these days, but I do try to find time for science as well. So again, thank you for coming. Thank you to the Jesus Foundation for enabling this visit. It's my 3rd visit to IAC, I think 4th visit to Tenerife. It's been a pleasure to work with Elena Jimenez's group all this time, and I hopefully will continue to be able to do so. Mandatory disclaimer is this presentation is while my affiliation is the National Science Foundation, I am not representing the views of the National Science Foundation giving this talk. So that's a mandatory disclaimer there at the bottom. Also, bear with me, this is my first talk in 2 years in person, and it's also my first science talk in 2 years. Hopefully this will go fine. So what I'll be talking about? I'll be talking about magnetic reconnection and why do we care? And frankly, if that's where we stop and you come out convinced a little bit, I think we'll do just fine. And then if we can get past that, then we'll go to magnetic reconnection specifically in weakly ionized or partially ionized plasmas. And we'll hopefully cover a few topics in that and why partial ionization matters in the dynamics of magnetic reconnection. So first, a very quick reminder, right? We're talking about plasma physics. We're talking about plasmas. So a cartoon on your left is sort of how you think about kinetic plasmas, meaning collection of particles, right? Which are charged particles, and they're interacting in that cartoon. They're all charged, so positive and negative. And you notice that the positive ones are a little bigger, heavier, probably, right? Protons versus electrons. So that's we think about a plasma as a kinetic plasma when we think about particles and distributions of particles. We can also think about plasma as a fluid whenever it's appropriate. Usually when there's enough collisions between particles, and then we begin to think about not just the particles themselves, but also waves. Right? So that's the cartoon on the right. And then the cartoon in the center is when all of that is penetrated by magnetic field. So that's a magnetized fluid plasma. So that's just kind of to set your head in the right frame of reference. And in a magnetized fluid plasma, the principal time scale that people usually think about, the fastest time scale, measuring stick, is the Alfvén, shear Alfvén wave time. So it's not the speed of light. It's this Alfvén time, which is the time it takes a shear Alfvén wave to propagate across a large scale spatial structure. Right, so you have some structure, and you're trying to the information propagates coarsely speaking, at Alfvén time, that's the fastest time it can propagate at. And then another parameter that will be coming up in the talk is what's called plasma beta, which is, you can think of as a measure of magnetization of the plasma, which is the ratio of thermal pressure to magnetic pressure in the plasma. So there are kind of two very basic things. We have Alfvén time, which is the time it takes signal to propagate, the fastest time, the shortest time, right? And we have plasma beta, which is measure of magnetization. So what is magnetic reconnection? Magnetic reconnection process is largely defined by a change in the topology of a magnetic field, right? So here's a cartoon of magnetic reconnection I stole off of internet someplace. And now I have a question for you. With that movie and that first bullet I put up there, what's wrong with that? What's not quite, what doesn't connect? Anybody? People on Zoom, there's some smart people over on Zoom as well, I'm sure. Anybody? So we're talking about change of topology of magnetic field. What's wrong between, why is that not quite correspond one to the other? Anybody? Can you define topology in this cartoon? No? Well, not really, right? Because you have no idea what's happening with these magnetic field lines out the bound. Right? I mean, I guess you can do some boundary integrals and do, but topology is not really well defined here. Right? So if I want to think about topology, I really do have to think about two field lines, right? So now we have two holes, right? Topologically, well, in 2D, right? I've got two field lines, so I have two holes. Now we have one hole. So I changed topology. So now I actually did tell you that what had just happened was a change in topology of the magnetic field. Right? And then there's a connection somewhere down there in the middle. So that's change in topology. It is a local reconfiguration and annihilation of magnetic field resulting in change of the global field topology. Just looking at that little box is not really good enough. You have to always keep in mind the bigger system. Even though, as you can see at the bottom of the slide, right, the standard 2D cartoon of reconnection is in fact just that little box. And I will in fact end up talking mostly about the little box later on. But you always have to keep in mind what it is, what's the context. Right. And so we can have this reconnection down there. We change the topology. So now what happens as a result of that? The energy that was stored in the magnetic field, I'll go back for just a second, right? So this magnetic field is a band, so there's energy stored in them. And what happens as a result of reconnection is that the magnetic field lines, which after changing the topology, that topology is then the configuration of the field is allowed to relax, releasing energy. So there's energy in the magnetic field, now you're releasing it. Right? Stress, energy stored in the stressed fields. It can be converted into all kinds of things. It can be converted into heating directly at the reconnection site. It could be converted into flows, waves, and shocks as a result of reconnection, which themselves then may convert into heat later on. It can convert into photons, radiation. And it can convert into high energy particles, which is, if you think about it in the fluid terms, it's kind of the Taylor distribution. It's the non-fluid part. So some particles which are accelerated to very high velocities outside of the general fluid description. So that's kind of the very, very basics of reconnection right there. You had magnetic field, which was stressed. Reconnection allows the topology to change. Energy is released from the magnetic field in a global sense, and it goes into the different other sources. Different other sinks rather of energy, right? So heat, photons, high energy particles, waves, and shocks. So now I will get to a little later. We can make this cartoon more complicated, and now we can say we have many magnetic field lines, many loops, lots of reconnection happening in a kind of quasi-turbulent regime. So there could be many magnetic field structures which are simultaneously interacting in many scales. So that's one cartoon. Any questions at this point? Any smart people on the internet? No? Okay. Yeah, I see one in the back. Yes.
Yes, we are always talking about here theoretically of the magnetic fields reconnecting. What kind of features in the sun solution you will find that there is reconnecting magnetic field in the world that you are
Very good question. Hey, I'll get there. Next slide. Any other ones?
I think you should not say that the Alphen time is the fastest one. It's just characteristic time. But of course, there are waves which are faster than the Alphen wave. Yeah.
Thank you, Peter, for that clarification. In general, that's absolutely true. But we will think here in a fluid sense, we will stick with my definition that we will think about the shear Alfvén wave as the fastest time in the system for the purposes of the stuff. But you're absolutely correct that in the kinetic description, there can be much faster waves. Any other questions or comments for that matter? No. All right, let's keep going. Okay, so as I just promised, here, why do we care, right? Why do we care? So magnetic reconnection, there's a couple of examples here, some movies. Two of them are observation on the center and the right. Well, the right, I guess, is more like experiment, and on the left, it's a simulation in very different environments. On the left, it's just one example. So, there are multiple examples one can find in astrophysics, right? Where magnetic reconnection, where magnetized plasmas evolve, and magnetic reconnection plays or is conjectured to play a role, right? On the sun, obviously solar flares, coronal mass ejections, the chromosphere, the solar coronal heating, space weather prediction. There are all kinds of questions that we want to answer, sometimes because we're curious, sometimes because, well, it's like space weather. It's kind of important, right, to know when to turn off the computer. So it doesn't burn up, or the satellite for that matter. So for all kinds of reasons, and then on the right, people are still trying to come up with getting the fusion energy thing to work, and that's quite important there as well, because it's again, it's a magnetized plasma with changes in topology. Here, this is just a few examples, and I'll go a little bit deeper in a couple of them. So in high energy astrophysics, I just pulled up two recent papers that involve magnetic reconnection, I'm happy to. By the way, I'm happy to share the PDFs of the slides with whoever, if you want to look at the links in the papers. On the left, you see a paper about gamma ray flares, right? And this is some observation with a cartoon of what the authors think might be happening in that jet coming out of a black hole. Right, and on the right, you see a simulation of a rotating magnetized black hole and magnetic island reconnection happening in the just outside the ergosphere of the black hole. What are general characteristics here? What's important physics in this high energy astrophysics environment? Well, it's relativistic, this is going to be my last slide with anything relativistic, but one has to think about general relativity. One has to think about high energy gamma ray flares. So energy, fair bit of energy is lost in electromagnetic radiation leaving the system. You can also, in some of these systems, you get actually peric radiation. So you get electric fields in your reconnection current sheets, which we'll get to a little later. You get electric fields which are so strong that out of vacuum, you get actually electron-positron pairs. And that's now you started with pure electromagnetic field, and now all of a sudden you have particles. And you'll see later on why that can become important when you're producing charged particles out of thin air, literally. Right? Oops, wrong way. In the solar corona, right? Again, I just pulled up a couple of recent papers. Observations of magnetic field and relativistic electrons along the solar flare current sheet, right? For beneath the CME, future CME flux road, there is reconnection and again emission of high energy particles, electrons happening is thought to be happening there at the reconnection site and around it. And then on the right, you see a simulation trying to explain how through a variety of interactions, now this is the kinetic description, which is appropriate for the solar corona, how electron acceleration may be happening through interaction of multiple islands. And if you remember, I showed you this cartoon, there's lots of things interacting. This is kind of where these things start. So you have multiple islands interacting and stochastically accelerating electrons that we can then observe. Let's see. Another example, interaction of the solar wind with planetary magnetospheres. I already mentioned space weather, right? That's usually you think about it in the Earth environment, but of course you can also think of it as a paper on the right, which is Saturn magnetic field, right? The interaction of the solar wind, and you have practical implications, certainly for the Earth, and then just we want to understand what precisely is happening. So interaction of the magnetic fields the solar wind coming from the sun, right? And the planetary ones produces all kinds of very interesting phenomena. Here again, in this, just similarly to the corona, where in the corona you have multiple scales. If I go back for a second, the big scales like that. Let's see. See this one, right? So the flux rho, people typically think about that on the MHD, the fluids scales, because you're getting to the scales of the system which are reasonably bigger than the collision space between particles on mean free path. But the reconnection is really more of a kinetic process, and that's the work on the right. So in a corona, it's a big environment, and usually you have to, which makes it very difficult, you have to think about both more fluid scales and the kinetic scales. Whereas in planetary magnetospheres, the collision mean free path is typically larger than the system size between electrons and ions, for example. So here, really much, very kinetic description is appropriate, and people begin to think about very carefully, and you can begin to measure it in situ, of course, about distribution functions of electrons and ions, and trying to match predictions to observations. So there's a lot of work. I just picked out a couple of papers in each context here. And then there is the solar chromosphere, and we will sort of gradually transition at some point in this talk to thinking about partially ionized plasmas. And this is a maybe overused cartoon of the solar chromosphere. And what you need to take away from it is that magnetic fields are everywhere, and they're all complicated and tangled up, right? And if you have magnetic fields which are all complicated and tangled up, they will be, in one way or another, will end up reconnecting, and you'll get the energy release from the magnetic field and various signatures. And so but it is a partially ionized environment, and that's what we will get to later on in the talk. Okay, so let's go through sort of a high-level timeline of what magnetic reconnection is, right? We have been talking about it, but now let's just summarize. So first, we have a free magnetic energy. We have to have free magnetic energy which is supplied into some large-scale volume. Right? A couple of examples. It could be pre-existing magnetic field structures that are convected towards each other. It was kind of like this first cartoon I showed you with two loops, right, which were sitting next to each other. Or it could be magnetic field which is stressed in place. So you can think about foot points of magnetic fields in a coronal loop, for example. Right? And this could be fast or slow relative to the Alfvén time, to my measuring stick. Right? Or it could be quasi-random on small scales, think nanoflares, or organized on large scales. Think about a CME going off of the sun. Right? So there are various possibilities. But the point is you're supplying magnetic field into free energy into the system, stressing magnetic fields. So then the magnetic fields begin to reconnect with each other over some set of small scale subvolumes. So you have big loops, but you have small reconnection sets. Free magnetic energy is released in the form of flows, heat radiation, and non-thermal particle acceleration. And there are various options of how it could happen. It could be released locally just within those small volumes, subvolumes, or globally due to the reconfiguration of the field. It could be released quickly or slowly, again, relative to the Alfvén time. And then whenever the free magnetic energy is exhausted, so there's no more energy that can be released, subject to various conserved quantities, right? Then reconnection ceases. So that's a kind of high-level timeline. You supply energy, reconnection begins to happen, energy is released into some other parts of the plasma, and then you're done. So when is there no reconnection? I was just saying that it's everywhere, always, all the time, right? Well, in vacuum, really, right? You can imagine you have two wires, right? You run current down two wires, you have magnetic fields in, let's say, vacuum, right? And magnetic looks just like reconnection in a way, right? You have magnetic fields. If you keep trying current, they're going to be going out and then beginning to reconnect. Well, that's not really interesting. It's just there's no response where that X point is. There's not really reconnection. It's just sort of boring. There's no energy being stored. There's no magnetic field being stressed. So there's nothing really interesting going on. Now, in ideal MHD, in the absence of magnetic diffusion, one can show that the topology is, so magnetic fields are frozen into the fluid, into the conducting fluid, in a perfect conductor, and the topology of the field cannot change. Okay, so the topology is exactly preserved. So you can't do that. So the truth, of course, always is somewhere in between the vacuum, i.e. no charged particles, and the perfect conductor, where the charges respond instantaneously to any electric field. And so everything that the examples I've been showing are somewhere in between those two cases. Highly resistive systems, one can argue it's sort of reconnection, but again, it's boring, because highly resistive system means that any stress in the field dissipates before any small structures form, right? So it's kind of boring. Everything is released diffusively on the global scale, and you never have these substructures form. And so there's one definition of magnetic reconnection, sort of thinking about it really in 3 dimensions, even though I can show you and will continue to show you most of the things in 2 dimensions. But again, you think about localized breakdown of the frozen and filled condition and the resulting changes of connection as the basis of magnetic reconnection. And connection here, it means that the plasma elements which are at one time connected by a single magnetic field line remain connected in subsequent times. That's hopefully it's similar to what I told you in the beginning of the talk. So what are the key questions in magnetic reconnection? How fast can the magnetic energy be released in different plasma parameter regimes, when the ratio of this magnetic diffusion time to the ideal Alfvén time, which is called the Lundquist number, can be very high. So in solar corona, 10 to the 10 or more. So the time on which things evolve in sort of MHD on the ideal time, and on which they can diffuse, magnetic field lines can diffuse, is hugely different. So how fast can energy be released when the diffusion is very slow relative to the ideal evolution? That's one question. Another question is, how is it possible that under some circumstances, free magnetic energy can be slowly accumulated and then explosively released? Right. So why is it not being released as it's being accumulated? What's going on, right? Why are we continuing to stress fields, and the energy is not being released, and then the solar flares happen on the order of minutes, right? And accumulates on the order of days and months, and then gets released on the order of minutes. How is that possible? What determines the energy partition? I've been telling you that the energy can go into all these channels. What determines the partition between thermal, radiation, bulk flow, and non-thermal particles? Right. And how is that related to whether energy is released primarily within the reconnection subvolume, so just at those localized sites, or if it's released really happening more globally? And finally, under what circumstances the reconnection subvolumes are localized in 1D, meaning it's a current sheet. So if you think in 3 dimensions, 1D localization means that you have a 2-dimensional plane, so a sheet through which reconnection is happening. 2D localization means that you have a line current. And 3D localization means that you have a kind of a point, like very small 3-dimensionally localized place where there's very high current density and where reconnection is happening. And so, all kinds of circumstances are possible. And what impact does that have on the global dynamics of a system undergoing magnetic reconnection? Right. So all the time you have to keep thinking about as we zoom in into these little sites of reconnection, we have to keep thinking about the big picture, the big system, because otherwise it doesn't really make sense. Any questions at this point? Peter?
I'm quiet. I'm enjoying your talk.
Yeah. Any other questions? If you're,
Question, but I
yes.
think I'll by the end because
Ask now.
I mean those pictures of relativistic reconnections that we've been shown, do they have any observational evidence that it actually happened?
Well, so as you can imagine, on the high-energy astrophysics side, it's very hard to resolve a reconnection site. But the fact is that it's very difficult to. So my understanding, and I'm not an expert really, but my understanding is that there are really no good alternative explanations for the observations of the gamma rays and sort of frequency at which they show up, how quickly the ramp up, and I'm sure there are people in the room and certainly this institute who know much more about it than I do. But it's my understanding is that at this time there are not very many, let's just say, other plausible explanations of the observed signals of the things they can measure. But of course, they don't measure magnetic fields directly. No, they can't measure anything like that. But it has been, again, so looking at it from a side, these theories seem to have been gaining momentum in terms of acceptance by the community of how important reconnection and this particle emission and gamma ray emission is in those processes. Anything else? All right, then I'll keep going. So some basics now, trying to move from sort of big picture cartoons to some details. So there's a classic magnetic reconnection cartoon or theory, which is now over 60 years old, and due to Sweet-Parker model. And we're back to the cartoon of 2D in the current sheet. And the way what this cartoon does, what this theory does, it does a very simple, in a way, analysis of what can happen in a two-dimensional system where you have these two structures, two magnetic structures, one on top, one on the bottom, with opposite magnetic fields that are coming together, interacting via the reconnection current layer, right? And so what can happen is there's reconnection that's happening there. The fundamentals of this model are that everything that flows in has to flow out. So this is a model in a fully ionized plasma, electrons and protons. That's the simplest thing you can do. And everything that flows in has to flow out. So you take your momentum equation, you take your continuity equation, you take your energy equation, and once you decide that everything that flows in has to flow out, you get certain relationships between the inflow speed, for example, of the plasma and the outflow speed of the plasma. You take your dissipation term that exists in that plasma for those parameters, and you come out with relationships of how fast reconnection can happen. Right? And one way to think about it is precisely how quickly is the plasma flowing in relative to how quickly it's flowing out. And the flow out speed, again, it's a magnetic field line that's bent here on right, the bent field lines, which need to relax. They relax on the Alfvén time scale. So that the outflow speed is basically set to be the Alfvén speed. And so then how fast the reconnection happens is really equivalent question to asking how fast is the plasma allowed to flow. And you can do the math, and what you get is that the reconnection rate ends up being a square root of 1 over Lundquist number. And again, the Lundquist number is the ratio of the Alfvén time to the resistive time. And I told you that in the corona, it can be 10 to the 10 or higher. You take this number and you get times which are many orders of magnitude slower than what's observed. So that's been a conundrum for decades, and there's been a lot of progress in figuring out why this is not a fully appropriate theory in this setup. But it's really the basis for just about everything that's been done, certainly in the fluid regime, which is what this is over the decades. I will point out here that here the current sheet, it's a single current layer. And you can, that was the original model, but you can really think of it as a kind of a box. It can be a current layer. You can now already begin to imagine with the previous cartoons I showed you that this current layer is not really a single current layer, but more of a diffusion box, which itself may be filled with little islands and little current sheets. It's really the box. So everything has to flow in, has to flow out. And in this model, the thickness of the current sheet is determined by the collision operator, diffusion operator. But if you begin to think about various structures inside this current sheet, maybe that diffusion operator is no longer determined by individual particle collisions, but determined by some stochastic processes. So that's that's the basic cartoon.
What is this model in 3D? Because in 3D you don't have a kind of sheet, right? You have a point, you have a layer.
Right. So in
Can you just repeat the question?
oh, sure. So the question is what happens to this model in 3D? What happens to the model in 3D? Very good question. Well, in 3D you may still have current sheets which are very long. So in some circumstances, 3D doesn't impact the problem. What happens in 3D when it's really not a current sheet that is very long in the out of plane direction in this picture, but is confined? Indeed, the model can change, and I'm not going to be addressing it in this talk, but I've done some work, and others have recently done more to think about to look at can outflows be in the third dimension, or even if this kind of patch or pancake of current that you get, which is localized now in 3D, if it can move, and what happens if that moves? So yes, there could be you can call them corrections or real acceleration of reconnection rate due to the three-dimensional nature of this. But for the purposes of this talk, in order to be able to get through it, we're going to stick primarily with 2D. That's a very good question. So what happens in partially ionized plasmas? Right? What's the difference? What's different in partially ionized plasmas from the cartoon I just showed you? Well, there are reactions between the neutral and the charged components. And I'm sure all of you appreciate that when we say partially ionized plasmas, you can have multiple species, you can have all kinds of funny things going on. But I'm more of a theorist, so we're going to make it very, very simple, right? When I'm going to talk about partially ionized plasmas, I'm going to think about a neutral, a proton, and an electron. That's the simplest model you can have with partially ionized plasmas. So, but between that, you can still have ionization and recombination, right? So there's reactions between ionized and neutral particles. There can be enhanced radiation transport and losses due to some excitations and all kinds of things happening with a neutral, for example, right? And during the recombination and ionization. And there can be drag and dissipation due to collisional coupling between the ionized and neutral particle populations. Right? So those are the 3 things that come in relative to the cartoon I showed you before, where it was just electrons and protons. Right? So these and other physical effects that I might have neglected to mention may be more or less important and may become dominant from both the dynamical system evolution and observational perspective, depending on ambient plasma parameters such as plasma composition, density, temperature, ionization fraction, and magnetic field strength. So I will try to convince you that this is the case in the remainder of this talk. But before we go there, let's come back to our key questions, just to remind ourselves what are the key questions in magnetic reconnection and how that's in partially ionized plasmas, right? So could the partial ionization effects impact or accelerate the reconnection rate? Could the partial ionization effects enable a transition from slow to fast reconnection? How do the partial ionization effects impact the energy partitioning for different ambient plasma conditions? And could the partial ionization effects impact the physics of reconnection region localization? Right? So these are just sort of same questions that I asked before, but really from a perspective of partially ionized plasma, how that may impact answers to those questions. So different rendering of the same cartoon, 2D, simple. In principle, everything that flows in has to flow out, in principle. It's a steady state cartoon, right? That's another aspect, it's a steady state cartoon. But now your continuity equation looks a little different, right? Not only, so if you look at any one species, for example, let's say we look at the ions and electrons as charged fluid, right? Things that flow in, some of them do flow out, but you also have a recombination and ionization processes. So, for example, you can imagine the situation in a weakly ionized plasma where the neutrals are an infinitely big bath. So let's say your ionization fraction is 0.1%, 0.01%, right? In your background. And so they're really an infinite bath of particles. And so you don't really have to think about them too much in terms of a steady state. You know, what's like getting more of them, fewer of them, they're an infinite bath. And now you can have reactions. You could have ionization and recombination for your charges. So not only, so if something flows in, an ion flows in, it doesn't necessarily have to flow out, it may recombine. And now it's gone. Just like I was saying in that.
But it can still move, no?
It can still move, but you don't need to worry about it because at that point it's no longer coupled to the field. So the fundamentals of the Sweet-Parker model, right, is that everywhere outside of the, I mean, everything has to flow in and flow out, but there's a coupling between the field and the charged particles. If something happens to recombine, if an ion and electron happen to recombine inside the current sheet, now your ion no longer has to flow out because it has disappeared. And as long as it's a very small ionization fraction, you kind of don't have to count that neutral anymore because it's 1 in a million. So it doesn't really make a difference. Right, so that can change the dynamics. So if the system is in ionization combination balance, if it is in balance, then there could be some enhancements to the reconnection rate, but really the single fluid analysis that I just showed you really doesn't fundamentally change. There's some factors that show up, but nothing changes fundamentally. If recombination dominates, then for the Sweet-Parker outflow bottleneck, and that's, if we go back to the Sweet-Parker model, the fundamental reason that the reconnection rate ends up being slow is because again, everything that flows in has to flow out. And the system can be very large on the inflow side, but it's limited to the diffusive scale in the outflow. So that's the bottleneck. That's what's referred to as a Sweet-Parker bottleneck. But now if particles recombine rather than having to flow out, you've gotten rid of the bottleneck. Things flow in, recombine, have no more plasma, can keep flowing in, recombine. If it was 0.01% of the population, nothing really changed with the neutral population, and your magnetic field lines are continuing to recombine, to continue to reconnect, while your plasma just disappears on you. Right? And I remind you of a connection to the high energy astrophysics, where you have situations of the opposite sense, where you could have these very strong electric fields, which break down vacuum, and now you have plasma being created. So there's some connections, even though the regimes are extremely different. But in the basic physics, there are connections. Now, so if ionization dominates with recombination, there you go, right? Now you have, all of a sudden, you're creating charged particles inside the current, just like I just did with vacuum, right? You're creating charged particles, and that, of course, will also change the dynamics. And there, what I will show you that the ratio of the electron density, ion to electron density inside the current sheet can become very, very large relative to the ambient conditions. So if you're interested, there's a bunch of papers that I've worked on with others over the last decade or so. But this last one is something that we've been working on last couple year, but we're finishing up last couple of weeks with Yelena and with Beatrice, who's been doing most of the work, by the way. So I'm just talking, but she's been doing most of the work. And that is really the subject of my current visit here this year. So just a few examples of reconnection in these partially ionized plasmas. We can take sort of a mid-chromosphere parameters in a high beta plasma in a null point magnetic field configuration. So what does that mean? That means that in a 2D picture, which is what I'm going to stick with, there is no large out of plane magnetic field. So I'm going to keep showing you that cartoon, right, with reverse magnetic fields, and there is no third component of the magnetic field. So here's some simulations of such a system. And what you see shown here is a density of the let's see, hold on. What's shown here, actually, take it back, it's not density, it's the flow velocities for the ions on the left and for the neutrals on the right. And you can see that the inflow velocities are different. So something's going on that's different from a single fluid description, where now you have these two populations and they're not moving at the same speed on the inflow side, but they are moving at the same speed on the outflow side. So we're getting something different, right? There's this decoupling there now with the two fluids moving differently, right? And it happens, not surprisingly, when the current sheet, when this diffusion region thickness becomes smaller than the mean free path of the collisions, which in this case is about 100 meters for these parameters. What else happens? If you look inside the current sheet, we've been talking about things inflowing, outflowing, recombining, and ionizing, right? So you look at these four quadrants, it's a symmetric problem. So you look at what's what, and you see that things are being supplied through the inflow. So the charged particles, the supply is through the inflow, not a big surprise. But the main sink is not the outflow, it's the recombination. So back to the sweet Parker, everything that flew, every charged particle that flowed in had to flow out, and that created the bottleneck, because the bottleneck was very narrow, it was diffusive scale. Now things don't have to flow out, they just recombine. That allows, so the particles recombine, that allows magnetic fields to reconnect, and hunky-dory, and we can reconnect much faster. So that's the basic picture. If you look at the cuts across the current sheet, right, you see that, well, we have a few features. We have the current sheet, which is here, which is indeed thinner than the neutral ion collision mean free path. So that allows for decoupling. You see some significant enhancements in the density of the charges in the current sheet, right? And ion inflow ends up being much faster than the neutral inflow. So that's that decoupling that I showed you before. So the neutrals are just kind of along for the ride for most of the time, but then it's just inside the current sheet, they're decoupled, ions flow in, recombine, magnetic field reconnect, and that allows for substantially faster reconnection rate than the sweet Parker production. Right? So, well, looks like at least in this regime, for this type of configuration, the partially ionized plasma allowed for faster reconnection than the classic model. So maybe it can solve some problems. And now let's look at another slightly different regime. We're now in the low chromosphere as in mid chromosphere. We have different densities, different, even smaller ionization fraction, right? A different plasma beta. And here we've been looking at the impact of different strengths of the magnetic field that's reconnecting in this region. Okay? And what we see is that with different magnetic field strengths, we end up with some like 500 Gauss in this case, we end up with ionization fraction increase from 0.01% in the ambient to half of the particles. So that's what, 1, 2, 3 orders of magnitude. More than 3 orders of magnitude, right? But what scales is that on? That current sheets which are 10 meters thick. Anybody here is brave enough to try to observe 10 meters in the sun? Probably not. But you have these, you're now forming these current sheets, right? Which have hugely higher electron density inside the current sheets than the ambient medium. And now you can already see a picture in your head where it's not just one current sheet, right? It's a whole bunch of current sheets inside some maybe bigger diffusion region. And you have these tiny clumps, but they're high, big spikes. And one can begin to think about what the signal may look like if you have lots of these types of current sheets, which have much higher density. Right? Now, the reason that happens under these conditions is because the radiation takes over. So under these conditions, you now have the ionization and the combination actually end up being balancing each other. So the reconnection rate itself within a given current sheet doesn't really increase in this regime. But what does happen is that your energy is lost. So this is now, it's a little bit a feature or whatever you want to call it of this particular model. We're looking at a small box, right? We're looking at a small box, and what's included in the model, which is certainly not perfect, but what's included in the model is optically thin losses. So that's what's included in this model. And if you allow for optically thin losses from your reconnection current sheet, turns out that all the energies that gets dissipated is lost, right? In some regimes, and that's what's shown here on the left in particular. Right, so all the heating is lost. So again, you now have not everything that flows in has to flow out in effect, right? You have energies that flowed in with a magnetic field, and then it didn't have to flow out; it was lost. So radiation. So what also you see in these simulations is that the temperature, for that same reason, because everything gets radiated, as long as there's some transitions between. Because this is a very simple model, right? There's no line. There's a little bit of line radiation that's embedded in the coefficient for the energy loss. But really, it's very simple. But as long as you can keep having these cycles of recombination and ionization, so electron keeps going up and down, up and down, up and down. And if it's optically thin, every time it goes up and down, you lost energy. So as long as you have both populations in this model, you keep losing energy, which also means you can't heat the plasma there, right? So for in these simulations for 100 Gauss and 500 Gauss fields, the temperature, there's more energy being dissipated, but it's all being lost through radiation, and so you can't get the temperature of the current sheet up much above 16,000 Kelvin. But once, if you crank up the field enough, you basically end up with a fully ionized plasma in the current sheet, and then all of a sudden it heats up. Because, well, now it's fully ionized. You're not losing radiation anymore. You're not losing energy to this optically thin radiation anymore. Right? Now, length scale here, notice this is now 100 meters is 1, and so these things are tiny. And so how tiny? So what we did now with this model is we looked at the hierarchy of current sheets. We took a system which is kilometer size and ran the simulation, and what we saw is that the current sheet breaks up into these plasmas and these substructures. And because our code has finite resolution and such, and the computers are only so big, we then, rather than trying to do that to infinite precision, we took rather a smaller system characteristic of a small current sheet in the bigger system, and then ran that. And that still broke up into plasma. It still produced a plasma. And then we took a smaller system yet, and we showed that, well, at that point it saturates. So the current sheet at that scale stops undergoing secondary instabilities. So what we really have is a cascade of secondary plasma instabilities, which terminates at a current sheet length of about 100 meters and the width of about 1 or 2 meters. So now again, we have the system. You can imagine you have these large scale current sheets, large scale magnetic fields, right, that come in and begin to reconnect. They form one current sheet that breaks up into little current sheets that breaks up into little current sheets. The smallest scale in thickness is about 1 meter. Your ionization fraction changes by several orders of magnitude between the regions on these very small scales. But maybe from the global perspective, your diffusion region is not this tiny 1 meter thing. It's really the whole box. Right? So now we change gears one more time, and rather than look at just these individual current sheets I was just showing you, we'll look at this work that we're trying to wrap up the paper on in the context of a Rayleigh-Taylor instability in the solar prominence. Right? So we have partially ionized plasmas, but we're really modeling a larger system now. We're trying to model really a thread in a prominence, but nevertheless here the units are orders of magnitude in terms of distance bigger than in the previous picture I showed. And here's an evolution of a Rayleigh-Taylor instability in a highly nonlinear state. We have these so-called fingers that form from instability. There's a magnetic field here in the plane that gets wrapped up around these fingers, and the fingers begin to interact. You form current sheets, and you have density structures. So I'll show you a movie prepared again by Beatrice, who does all the work. And it's just a little bit at the end there. Right? And let's see, I think I need to keep clicking on it, and you can watch it and see. So what you see here is on the left, it's the density of the charges, so the charged part of the fluid with magnetic fields around it. And the arrows, I believe, are the flows. And on the right, you see the neutral density. They're not quite on the same scale. It's about the order of factor of 3 between the two color schemes. But what you see, for example, is, well, you see the connection here in the current sheets, and we'll zoom in a second. You see formation of these bubbles, plasmoids, right? Where now, if you can look at here on the left, the density of the charges really went up by a factor of a few between the initial state and the final state. And then there is this large gradients in neutral density as well. And there is these clumps of high density and really bubbles of low density of neutrals that begin to form. Okay. So here's a zoom in of one current sheet. Well, really, not really one current sheet. It's one box. And as you go through in time, right, from left to right, you see that, well, one current sheet forms, but then you can even begin to see right here, and as it goes, I don't know if you can, yeah, we can make it out. The plasmoids begin to form, they begin to be ejected, new plasmoids form, and further ejected. So in this system, we see the sequence, this recurring sequence of generation of plasmoids that are rejected and then themselves merge into this bigger island sort of on the bottom of the picture. And this forms real electron density clumps of plasma. We looked at the spectrum sort of in space, both magnetic fields and charge density, and we see saturation in the spectrum of the structures. So that's something interesting that well, may be observable. So what's the takeaway message? Well, first of all, magnetic reconnection is a ubiquitous process in magnetized plasma. So hopefully I've gone some way to convince you that indeed it's a process worth studying, and it is important both from a fundamental physics, astrophysics perspective, and in fact from a practical perspective as well, of predicting things like space weather, maybe developing fusion energy someday. In a partially ionized plasmas, where you can have dynamic non-LT plasma evolution, right? Non-local thermodynamic equilibrium in a current sheet that can lead to resistivity independent reconnection and or very rapid radiation losses in those current sheets. Localized production of highly ionized plasmas with orders of magnitude electron density enhancement over the background is possible within current sheets which are much thinner than observationally resolvable, certainly in the sun context. One might be able to do some experiments in the laboratory, but that's not easy either. We have very high aspect ratio current sheets lead to formation of secondary plasmoids, or flux ropes in 3 dimensions, which initiate this cascade that terminates with current sheets not just much thinner, but much thinner than observationally resolvable. Now we're talking meter scales. But again, this you have this. You can imagine again. You have the sea of little current sheets with hugely varying electron density. But if the sea is big enough, maybe you can see this, you can observe the sea, but you have to figure out what it is you're going to observe when it's not uniform sea, right? It's a sea of lots of little spikes. And finally, magnetic reconnection in a turbulent environment, mixing cold, mostly neutral material with hot, mostly ionized plasma, such as in the Rayleigh-Taylor instability, can produce a stable spectrum of high electron density structures that actually may be observable, because now we're talking about bigger scales. And so, you know, that's what you guys are good at here at the Institute. And luckily, I don't need to worry about it. So with that, I think that's all I had. And I'm even on time. So thank you. And I'm happy to take as many questions as you have.
Oh, thank you very much. So maybe we can start already with the question to the room with the reasoning, and then we'll go on to one question. So is there any question in the room?
Don't be shy. There is no such thing as a stupid question.
I have many questions. I mean, I get some opportunity to ask him.
You can start and then.
I can start. Well, I can start with this idealized model that you showed. I mean, just your old paper for the connection. When you say that finally you come to have inflow of ions to the current sheet, or the current sheet to be higher speed than the neutron, what's actually the boundary conditions for both of them? I mean,
at the outer boundaries, right? Right. So the outer boundaries. So very good question. Let me describe the setup. So I will show you a zoom in, of course, of the current sheet. The setup in all of these two-dimensional simulations is such that the box is very large in the outer plane direction relative to the thickness of the current sheet or any of those scales. We are not doing in these simulations, we did not do what I showed you at the very beginning, like two loops or two flux ropes that are merging. Right? The boundary conditions are far away, but it's basically a constant field far away. And we will look and make sure that that the system is big enough that all flows can freely close, and we're not defining what will get our result by our boundary conditions. So you make the box, right? The way you do it always is you make the box twice as big in that direction and see if anything changed. If nothing changed, you're probably okay. If things changed, then you're probably not okay. So we've done that test and we made the system, the box twice as big in the direction of the inflow, and things don't change.
So the velocities are zero.
Very far away, yes. Very far away, they're zero. That's correct. In this setup, so in these setups, the energy of the magnetic field, the free energy, is initially embedded in the system with these reverse magnetic fields, which is different, and that's a good point to make here, which I didn't make. If I go back to this picture, right? This is a global system, and now the current sheets form self-consistently and naturally. And what we think is happening here, it's a little different. That is, in these earlier setups, again, the free energy was already in the system, and it relaxed at the rate at which it wanted to relax. That setup does not answer the question at all. One of the questions I posed, which was how the energy can be built up slowly and then released quickly, because we just create the system from whatever you believe in, we just God, and you put the energy there, and then you see how quickly it can relax. This system is different, which is right. The energy is being supplied self-consistently through the big global evolution, and in fact, we believe, we have evidence which I can show here. But wait for the paper, that this is a driven system. So the reconnection in these little current sheets is driven by the global flows. It's not that you build up energy, magnetic energy, and then it gets released. The flows are actually driven by other things as opposed to self-consistently forming. That was probably the answer to two questions, but okay. Anything else? Come on, folks. You must be curious about something.
I will ask a question. I'm not alone in the field, so I know one of the big questions about solar physics is the heating of the core. So is it kind of giving some idea of if it's really contributing to the heating of the core, or it's not enough?
Very, very good question. So I think it continues to be an open question. Right? People keep closing it every 5 years, they claim to, and that continues to be an open question. I think magnetic reconnection is certainly one of the, I don't think anybody would honestly argue that it's one of the contributing factors in some way. Whether it's dominant in some regimes or not, I think is very much an open question, right? So people talk about so for example, people talk about waves coming out from the photosphere. Right, through the chromosphere somehow maybe, and then damping and heating. So those waves could come from convection motions and all kinds of things that are not directly related to reconnection. But in fact, there are some models which show that part of it, even of those waves, can actually result from reconnection current sheets, let's say in the chromosphere. So it's it's a lot of people tend to, as I mostly did in this talk about magnetic reconnection and isolation. But I try to keep referring you back to the fact that in any practical systems, a reconnection site is just one piece of the bigger puzzle. And whether you want to call it turbulence or you want to call it waves or whatever you want to call it in a sufficiently complex system, you're going to have multiple reconnection sites. You're going to have interaction of waves and reconnection sites where waves may produce reconnection may produce waves. And so saying that it's waves that are heating or it's reconnection that's heating, I think in most cases will be a false choice. In some cases it might not be, but in many cases I think it will be a false choice. Because even if you think about a little flux rope, twisted up flux rope, you can think about, okay, the flux rope is going to oscillate and become a wave, and that may be getting damped and maybe heating the corona, the chromosphere or whatever. Well, in that twisted up flux rope, quite likely there's going to be small reconnection sites just because it's a twisted magnetic field. And so what does that do? That may be generating some of the waves. So don't think there's a clean answer to your question, other than it's complicated. But I think it's definitely a contributing factor, but it might depend on the nanoflare models or all kinds of models that people put forward.
Is there any other question in the room? So maybe we can switch to
these students are really, I keep interrogating them when they come here and they don't want to ask a single question. All right.
So maybe someone remotely had a question. So if so, raise your hand or write it in the chat. Question is,
I forgot how to raise my hand again. I apologize. So I speak directly. I don't know where is the raise hand button again on my computer. So Slava, it was very nice talk. I really enjoyed it. It was very nice. I have basically what I want to say is though that the problem is really difficult to study, because as you are showing, it goes to tiny and tiny scales. So basically, we are trying to study something which depends heavily on the dissipation mechanism, and we do not have the correct dissipation mechanism. Like you were, for example, saying that ideal MHD, there should be no magnetic reconnection, but you cannot do ideal MHD simulation. You need to have some dissipation. So you simulate the MHD and there will be reconnection at some scales. So then you will say, oh, this is not good. So we have to go to smaller scales. There will be whole term. There will be the stress tensors, heat fluxes. It might be overall an ill-posed problem to study the reconnection because it happens in such a tiny scales. No? What do you think?
So I would disagree that it's an ill-posed problem. It is definitely a very difficult problem. And I quite, because of the subject of this talk, I avoided largely the kinetic aspects, right? But as I didn't mention, let's say in the Earth magnetosphere and even in the corona, right, you very quickly get to the scales where the fluid approximation is no longer valid. So if the fluid approximation is really not longer valid, and we can do whatever heat fluxes you like, it just doesn't work. And why does it not work? Because at some point, at some scale, if your number of electrons and protons, let's just say, is sufficiently low, but they're there enough to conduct electricity, the Larmor radius of the particles, especially if it's a null point magnetic reconnection where there is a location of zero field, the Larmor radius of the particles, well, it's going to be non-zero. It's going to have a finite value, right? And for ions, it's going to happen faster than for electrons. Why is that important? It's important because how do we describe when we talk about a magnetic field line? What do we actually mean? I mean, theoretically, right, you can write a vector potential, you can track the vector potential, and you can define a magnetic field line that way. But more practically, it's really the thing that the charged particle rotates around. I mean, that's how you can see the magnetic field line, right? It's what your electron is going to spiral around. Well, if you have a magnetic null, then at some point there is no field to spiral around. And so the trajectory of the particle will become basically, it's going to have all kinds of funny shapes. So there is effectively a region where you cannot cleanly define, in a really meaningful sense, a field line. All right? And again, you can do it kind of through a vector potential, but practically speaking, you can't really define the field line anymore. And so that region I would refer to as again, in some way, a diffusion region. You still have magnetic reconnection because it's still going to be a very small region relative to the system size, right? And so I can go back to the very beginning of the talk. Maybe I actually should, right? To the early definitions and cartoons. Which one? I'm going to like first this one, all right? That when we talk about reconnection, we really should always remember that we're talking about a very small region which enables the reconfiguration of the global field. So in that sense, it's a fairly well-posed problem. But as you start zooming in and zooming in and zooming into that box, indeed things become very complicated. And I think the emerging consensus of the community that studies this in different regimes is because in a fluid sense, for example, of these various secondary instabilities that they demonstrated and people have recognized that they exist now they've been postulated even earlier, but they've become quite well recognized in the last 10, 15 years, that thinking about these single current sheets in a big picture is not particularly useful. You may still want to know what's happening in each one if you want to do some statistics to understand what to look for in this bigger diffusion region. So it's not a completely useless exercise. But to think about the bigger picture, you really do need to think about a bigger region than a single current sheet that likely does involve multiple structures. So I don't know if that answers your question or comment, but I certainly agree with you that it's a very complicated and interesting problem. And I only touched on one piece of it, and so I gave some hints to other circumstances, other environments where there are other effects that may be important as well.
Thank you, Slava. Yeah, it was I agree with you with everything you said. Yeah.
Wow, I think I've achieved something. Any other comments or questions, folks? Yeah. Speak up.
Can you comment about human battery effect? Because current sheets you have very small scale. Can it be important in astrophysical sense? Because I mean, it's known that it's on larger scale, it produces very small magnetic field, but in this configuration with a very thin layer, can it be important?
So let's see. I mean, I haven't thought about this very much, but I guess I think the way that may relate here is through the relaxation of the magnetic fields, right? Which may be generated through Biermann battery, right? Is how they will then relax into some bigger structures. But we should probably talk more because I'm not entirely sure I understand the question. It's not something that comes up very often, certainly in the context of kind of thinking about just the reconnection current sheets and such. But I'm curious what you're thinking, so we should talk more.
Any other question here or remotely? Okay, if not, let's thank Slava.
Well, thank you.